Hello everyone. At first, I would like to thank the organizers for providing this opportunity for me. And today, I'm going to introduce algorithms for approximating means of semi-infinite quasi-Toeplitz matrices. This is a joint work with Dario, Bini and Bruno Iannazzo. Okay, first I would like to introduce the Toeplitz matrix and quasi-Toeplitz matrix. So if given a function a of t, and suppose a of t has this Fourier series, and this t is in the set 0 to 2 pi, then a Toeplitz matrix associated with this function a is defined in this way. And we call the function a the symbol associated with this Toeplitz matrix. Then we define the class Qt of quasi-Toeplitz matrices as a set Qt. The matrices inside this set is the sum of a Toeplitz matrix and a correction matrix. And here, the symbol a associated with this Toeplitz part is a continuous function, ranges in the set 0 to 2 pi, and f0 is equal to f2 pi. And this correction matrix K is a compact operator in the L2 space. The L2 space is a vector space where the true norm of the vector is finite. And using this definition, we found that the set Qt is a subset of the set of bounded linear operators from the L2 space to the L2 space. And for any quasi-Toeplitz matrices, we call T of A the Toeplitz part of A, and we call K the correction part of A. And in what follows, I will use Qt to denote the word quasi-Toeplitz. Here are two important properties of the Qt class. The first one is the Qt is a Banach algebra of operators in L2 space. This means that the Qt is a Banach space, and the norm is submultiplicative. Another important property of the Qt class is that it is a C-star algebra. So this means that the Qt is a Banach algebra with an involution that satisfies these four properties. Okay. This property is very important because since Qt is a C-star algebra, so that we can use the continuous functional calculus. In fact, if T of A plus H is in the Qt class, and suppose it is self-adjoint, and suppose f is a continuous function defined on the spectrum of Ta plus H, then this function, then f of T of A plus H is well defined, and we prove that this matrix is again a quasi-Toeplitz matrix, and the symbol associated with this Toeplitz part is the composition of f and a, and this matrix K is a compact operator in the L2 space. And if f takes real values on the spectrum, then this matrix K is self-adjoint. As a useful corollary of this theorem, we found that for a quasi-Toeplitz matrix, which is positive definite, then the piece root of A exists, and the piece root of A is in the Qt class. Okay, now I'm going to introduce means of matrices and means of operators, and we start with means of matrices. So given two matrices A and B, and suppose A and B are positive definite, and if we give a parameter t, which is in this unit interval, then the weighted geometric mean of A and B is defined in this way. And you can see this definition involves the square root and the teeth root of some positive definite matrices. And when t is 1 over 2, we get the well-known geometric mean. And this is the definition for geometric means of matrices. And we found that using continuous functional calculus, this formula makes sense for bounded self-adjoint positive definite operators. So that for positive definite QT matrices A and B, this weighted geometric mean of A and B is well defined. And using the continuous functional calculus, we prove that this mean is in the QT class. Okay, now for the Karcher mean. So first give positive definite operators A1, A2 to AP. And they are bounded linear operators from the L2 space to the L2 space. Then the Karcher mean of those operators is defined to be the unique positive definite solution of this operator equation. So when those A1 to AP are matrices, the Karcher mean is well defined. And for the case where those matrices are infinite dimensional operators, it has been proved that the Karcher mean exists and is unique. And we found that in some certain applications, like in the reader detection, the matrices to be averaged always have the Toeplitz structure. And in practice, they are large-scale Toeplitz matrices. So, as a natural question, we would like to ask, if the matrices to be averaged have a very special structure, then does the mean preserve the same structure? Okay, to answer this question, and in our paper, we studied the Karcher mean of infinite dimensional quasi-Toeplitz matrices. This is because in a recent paper, we found that techniques developed for the geometric means of infinite dimensional quasi-Toeplitz matrices are effective for large-scale finite-size Toeplitz matrices. So this enlarges the range of applications, including all cases where large-scale Toeplitz matrices should be averaged. Since we are focusing on the positive definite operators which has this Toeplitz structure, so we wonder if the Karcher mean have the same structure. So the answer is no. In general, the Toeplitz structure is lost since the multiplication of Toeplitz matrices is not closed. But we found that a quasi-Toeplitz structure is preserved. And here are two main results we obtained. The first one is we show the Karcher mean of QT matrices is in the QT class. And then, after fully exploring the QT structure, we provide numerical algorithms for the computation of the Karcher mean. Okay, first I would like to show a constructive proof that Karcher mean belongs to the QT class. And we need the help of another mean we call power mean. And the power mean of the matrices A1 to AP with a parameter S, which is in this interval, is defined to be the unit solution of this operator equation. And with the help of the power mean, we can prove the Karcher mean is in the QT class. Here is a sketch of the proof. At first, the power mean converges to the Karcher mean in norm as the parameter S goes to 0, and this has been proved in a recent paper. And then we show the power mean PS for any S belongs to the QT class. And finally, we use this useful result in this paper. It shows that if a sequence of quasi-Toeplitz matrices converges to a bounded linear operator A in the true norm, then this limit A is in the QT class. So using these three items, we can prove the Karcher mean is in the QT class. And the first and the third item has been proved. So the key point is to show the power mean is in the QT class. So this is not difficult to show. To show the power mean belongs to QT, we use this iteration. The starting point x0 is chosen to be the arithmetic mean of the matrices A1 to AP. And this construction of the iteration is not difficult. We know the power mean is the unique solution of this equation. So using this equation, we can construct an iteration. For example, here it is xk, then we get the xk plus 1. So if this iteration has a fixed point, then the fixed point is the power mean. And we found that for the sequences generated by this iteration, the matrices xk at each step is in the QT class. And we proved that the power mean is in the QT class. And the symbol associated with this Toeplitz part is expressed in this way. It is easily to obtain. And we show that the sequence xk converges to ps, the power mean, in the true norm. And in detail, we show that there is a convergence for the symbol and there is a convergence for the correction part. For each xk, we have a symbol function xk, and we show that the sequence of the symbol converges to the symbol of the power mean uniformly, and the sequence for the correction part converges to the correction part of the power mean in the true norm. And in addition, using this convergence result, we can get more information for the convergence rate. In fact, for the convergence of the symbol, we have this inequality. And this inequality proves that the convergence for the symbol is linear. And this again shows that the convergence rate for the whole iteration is at least linear with a rate 1 minus s. Okay, now we have shown that the power mean is in the QT class, so we can let the parameter be 1 over n. Then for each n, we know p 1 over n is in the QT class. And then using this result, when n goes to infinite, the power mean converges to the Karcher mean in the true norm, so that the Karcher mean is in the QT class. And we found that the symbol j associated with this Karcher mean is the geometric mean of the symbols of A1 to AP, and A1 to AP are the symbols of the given matrices A1 to AP. And again, we found that for the sequences of the power mean, we have a sequence of the symbol, so we found the symbol converges to the symbol of the Karcher mean uniformly. And using this convergent result, we found the convergence rate. Actually, for the convergence of the symbols, we have this inequality, and this inequality suggests a sublinear rate of convergence of p1 over n to the Karcher mean. And this also shows that the convergence of the power mean to the Karcher mean is linear, so it's very slow. So to achieve a faster convergence, here we propose to approximate the Karcher mean by using the Richardson-like iteration. The Richardson-like iteration is like this, and you can see that at each step there is a parameter theta k. This parameter is required to be computed at every step. And this method works well for the finite-dimensional case. You may find it in this paper. And we found that this iteration can be applied to the positive definite QT matrices. But there are still two important issues left. The first one is how to choose the starting point x0 and how to find an optimal parameter theta k at each step. Okay, concerning the choice of the x0, in fact, any positive definite x0 is okay for this iteration, but we prefer a choice of x0 that is quite close to the Karcher mean, so that the convergence is faster. So a possible choice is the chip mean, which is the common limit of these sequences. And if the starting point is chosen as a QT matrix, then this iteration yields a sequence in the QT class, so that the chip mean is in the QT class. This means that the starting point for the x0, is a quasi-Toeplitz matrix. And for the choice of the parameter theta k, we actually it's difficult to get the optimal value, since the optimal value requires the eigenvalues of the Karcher mean. But Karcher mean is the one that needs to be computed, so that we provide a better evaluation of the optimal value in this way. And this choice has been implemented in this paper. Okay, and we prove that this choice also works well for the QT matrices. And using these two choices, we give some numerical tests to show the efficiency of the Richardson-like iteration. Here for the matrices AI, I equals 0 to 6. This means that we give 6 positive definite quasi-Toeplitz matrices. Then we use the Richardson-like iteration to compute the Karcher mean, and x0 is the chip mean. The computation for the chip mean takes 3 steps, and the Richardson-like iteration takes 22 steps. The overall time for the CPU is 133 seconds, and in this test, it shows that the Richardson-like iteration works well for the computation of the Karcher mean. And this figure gives an idea of the structure of the computed Karcher mean. This means that even though the Karcher mean is of infinite size, but if it has the quasi-Toeplitz structure, then it can be approximated by a finite number of parameters. Okay, this numerical experiment shows the convergence behavior of the power mean to the Karcher mean. This one shows the convergence of the sequence xk of the fixed point iteration, here this iteration, and we know that the convergence is linear. And this numerical result coincides with the theoretical results. The convergence is linear, and the smaller s is, the faster the convergence is. And this figure shows the convergence of the power mean to the Karcher mean. And you can see the convergence is very slow, it's linear. Okay, for the conclusions, we show that the power mean preserves the quasi-Toeplitz structure if the matrices to be averaged have the quasi-Toeplitz structure. And we show that the Karcher mean of positive definite QT matrices belongs to the QT class. And we provide 2 numerical iterations for the computation of the Karcher mean. The first one is based on approximating the mean as the limit of power means, and the second one is based on extending to operators the Richardson-like iteration, and the latter iteration is faster. Here are some references. Thank you for your attention.